Alright, hell yeah. So sit back, relax. I think we have a good one. A subscriber wanted me to do this problem. And I decided to actually spend some time on this. And we're going to do it, you know what I mean? Like we're going to teach the subject. So hell yeah. And this involves differential equations and calculus. And I think that anytime I see like a D, I think like that's the grade I'm going to get in this class. You know what I mean? And so, and we're just slowly, like I've graduated college and just coming back to this calculus, you know what I mean? It takes a while to kind of get an intuition for it, but I think we're doing pretty good. So hell yeah. So this problem, and let me sit down. Oh yeah. So this problem is going to be set up where we have a huge hemispheric bowl. So I threw this into Google AI, like, hey, give me a hemispheric bowl that's 9 feet in radius. You know what I mean? This would be a perfect thing to skateboard. So for our problem, it's going to start brim full. And then it says in a half an hour, it's going to almost reduce the height by half. You know, it's going to go from 9 feet to 4 feet. So more than half the height. And this is where, you know what I mean, what do we know about a sphere? It's shaped like this. So if we go half the height, that's most of the water. You know what I mean? And if we even go past half the height, that's even more than most of the water. Alright, so we got a good visual on that. This problem is going to use Torricelli's law. And it's kind of fascinating because if you Google Torricelli's law, and we'll get into it in a second, that's going to be ideal. Like water is like literally free falling, you know, and we'll talk about that. But if water was dropped from a height of 9 feet through this hole, it would have a speed of, you know what I mean, if you drop a rock from 9 feet and then it goes through a hole, it has some sort of velocity leaving that hole. Well, this Torricelli's law is going to show that the water is leaving the hole at that drop velocity. Now, as the water level goes down, it's like you're dropping a rock, you know what I mean, from a little bit lower. So after half hour, the water in the tank's only 4 feet. So that's the equivalent of like dropping a rock from 4 feet, and that's going to be the velocity of the rock through the hole. And that's a good way to intuit that that's going to be the velocity of the water. Now we are going to go into Bernoulli's equation to kind of show that. So we do everything. This video is juicy. And then Torricelli's law isn't an ideal, you know what I mean? But they're going to say we're going to use Torricelli's law in this form. So this 0.6 is going to be not ideal. And if you're not familiar with Torricelli's law, you know what I mean, it would be get rid of that. But now we're gonna say this is only like 60% efficient, maybe. You know, the velocity coming out. Well, and what is it? That's why reading differential equations are a bummer. But this says that the change in the volume of the pool, and then anytime you see a differential equation, this is the first thing I'm going to write. You know what I mean? We can turn this into like a delta. This is capital delta, the Greek letter delta. And, you know, it's a change. And it's a quantifiable change. You know what I mean? Now my mind's not thinking about the infinitesimal. And, you know what I mean? Maybe the third Ant-Man movie. Anyway. But hell yeah, when you put a delta on here, you're like, hell yeah, this is a serious change. I can visualize that change. And why not, if your problem allows, make your change and... See, I even messed it up. I even put a change d. This is how little I am aware of this little d. So hell no. This is going to be change in velocity divided by change in t. And what I was getting at is if your problem allows, and you can have your change in t be 1 second, well, hell yeah, booyah. Now, this is almost like it goes away. Now, it doesn't unit-wise, I mean, because this is still a second down here, but it's a proportional, or I guess, you know, it's basically just like your change in velocity. So now you have a change in velocity every second, let's say, and that's equal to this equation. Alright, hell yeah. And I have not done this, but I think the first thing to do is just wrap your mind around units. You know what I mean? So right here, this is the acceleration due to gravity. That's going to be in meters per second squared. This is going to be your height of the water. That's what they're going to say y is. So on this, you're going to have a coordinate system where this is the y direction, and this would probably be the x direction. Okay, and then that's going to have units of meters. So now this is going to be meters squared, second squared. And when we take the square root of that, we're just left with meters per second. So here's a velocity term. Now over here, here's another distance term, so we have meters squared. And then, okay, sweet. And then we see that we have meters squared times meters. So we have meters cubed per second. And this is what the units on this are. We can say change in volume and then change in time. So now we have our, at least our units. I think that is kind of the first, that was very useful even for me to do right now. Alright, hell yeah. And I think one way for me to envision calculus problems, rate problems, differentiate, like what are we doing? You know, is it all, you know, it's like differentiating, integrating, how does it all work? Like what I'm going to get to is like the Excel spreadsheet. So maybe we'll dive into what this but I guess how do I say that in just a few sentences? Is if I can just boil this equation, and I did it to solve this, if I can just boil this equation to be like, hey, for every 1 second, this is my change in velocity. Like that's going to be a number, and that's going to be in meter. And I'm sorry, this isn't velocity. Holy hell. Change in volume. Okay, so let's slow down. So this equation, if I'm going to run it for 1 second, I do that kind of a lot, especially for, you know, projectile problems or even force problems. Hey, run a force for 1 second and just imagine that it's going to be that way for the entire second. You know what I mean? Because this is constantly changing. You know what I mean? If I say I run this for 1 second, you're going to get the wrong answer. But that's where it's close enough. At some point, it's going to be close enough. And then here's another aspect. Is like my brother is like doing quantum physics. He's working with lasers, and he always has to use, you know, kind of the wave function equations. And they don't play ball with closed form solutions, right? I mean, I don't even know if I'm saying that correctly, but basically, you know, they're differential equations that just can't be, you have to use numerical methods. So that's what we're doing in Excel. And if you do use numerical methods, even though that sounds like it's going to be difficult, and that was a 400 level class that I took, and it was actually really easy, and I was just like, whoa, this is like real easy, and it makes sense. Why aren't we learning this? Because it's just time consuming maybe to like, you know, spend some time going over those processes. But it's so tangible because you're just like, hey, I have something that changes. Well, let's just assume that even though it's constantly changing, we're just going to be like, well, let's just get a value and say it's consistent, you know what I mean, for this much time. And then if it changes value, cool, it's going to be consistent for that much time. And you know what I mean, that's kind of what we're doing. And if we made those changes real small, hell yeah, we'd graph in some function and whatever. But this is the basis of calculus. And I think if you don't if you do use these moments to be like, hell yeah, these are your aha moments. To be like, oh, if I run this for 1 second, if this drains for 1 second, this equation is giving me the change in velocity. So let's even just write it. So and what does this equation says? This equation is going to be the change in, and I keep saying velocity. Really apologize about that. It's the volume It's capital V. That's going to get me every time. But it's the change in volume of this pool. And even just like looking at an equation, now that we simplified it, we kind of took away the derivative. That might have been complicated. But now we just like, hey, we're going to run it for 1 second. So we literally have change in velocity. Let's at least write it one time. Is pi r squared square root 2gy. Now let's look at this equation. We have the change in velocity, and then you ask like, well, what is it a function of? And I think more appropriately, and we'll see if we get into the literature or just kind of how I solve this problem. So how I started to solve this problem is just like, well, what changes? So all I have is this written down, and I wrote it down again. But here, and we said we ran it for 1 second, so we're kind of, just saying it's a change in volume. Got that right. And then I'm just like, okay, what changes? Well, this y, and then even some of these, it's really tricky. If you got this in a test, and then you just weren't familiar with using height as y, that might trip you up. Or the opposite, if this was h and you just weren't used to it, just as I think calling it h might be a little simpler. Calling it y, that seems like it's maybe more complex. But anyway, so the height, this is the height. And hell yeah, the height changes. Now for this problem, it says, and this is where we're going to be done with this page, because this is another aspect of problem solving. Why not take the problem and just get the nitty-gritty? We really didn't read this, but like at a certain time, the hole is opened. A hole of unknown radius is opened. 30 minutes later, the depth of the water is now 4 feet. And then we're going to use Torricelli's law, which is an ideal state, but we're going to use this constant of 0.6, meaning that it's only 60% ideal. Maybe you'd say it that way. And then we want to know when the tank, at what time will the tank be empty, and what's the radius of that hole. And for whatever reason, maybe you could solve them in that order. I would assume that I would need to solve but I don't know. I just solved the radius first, the radius of that hole. Okay, hell yeah. So this is one way to kind of simplify what we got going on. We have this hemispheric bowl. I can remember that it's a hemisphere. It has a radius of 9 feet. It's brim full. I can remember that. We have a hole at the bottom. That's a radius of r. So now this hole is a circle, and it's got a radius of r. So if I wanted to find the area of that hole, it would be pi r squared. Keep that in mind. And then the time was half an hour. So that's going to be 30 minutes. And in 1 minute, use factor label method, is 60 seconds. So seconds cancel. This is an equivalence. 60 seconds is 1 minute. And then we get 3 times 6 is 18 with 2 zeros. So we get 1800 seconds. All right, hell yeah. And then at that time, the water in the bowl, hemispheric bowl, is 4 feet. Cool. We want to know the time when the tank is empty, and then the radius of the hole. Booyah. All right, hell yeah. So this is kind of how I started solving this. I was just like, well, what part of this equation is constant? And so that's why we went back, because the radius of the hole. The radius of the hole ain't changing. Gravity isn't changing, because we're not moving that far. You could be on top, and that's just good to know when gravity does change. Whether you're on top of Everest or at the bottom of a trenchy trench or whatever. Basically sea level to Everest, whatever. 9.8, 10, who cares? That ain't changing. So now this really simplifies it. So the first thing that I did to this differential equation, just because if you are going to use calculus, I think there's 2 aspects of calculus. One is what we just said. It's just like, what the hell does this even mean? It means that the volume is going to change given, and this is all differential equations. They're like a change in something, over a change in something else. And so we got 2 different things. So usually this is going to be like time. For our problem, if we did chain rule, we could have the change in the volume with respect to the change in the height, and then change in the height with respect to change in time. So that's the chain rule. And then what I do enjoy, like once you get used to the calculus, is like, hey, this is saying like 2 divided by 3 times 3 divided by 1 is the 3's cancel, and we just have 2 divided by 1. And you had, you know what I mean, you had 2 divided by 1 the entire time. We were just, yeah, so I do enjoy that aspect where, you know, the laws of math aren't bizarre or anything like that. But I swear, even with differential equations and integration, it seems like bizarre stuff's happening. And it's just like, where am I in the process? I'm always trying to ask that question, like, where am I in the process? I can't explain what the hell's going on. Hell yeah. And it's always a bummer when it's like this part of the process. You're just like, I see a differential equation and I really can't tell you what's going on. But I think we're doing a pretty good job. We're like, hell yeah, we have a change in volume of that pool every second. You know what I mean? So that's kind of how I'm saying it or phrasing it. And we already said that change in 1 second isn't exactly true, because it's not a differential time. So we're going to get something like that. It's like, here's going to be the change in volume. It's going to be that number. And then at a new time, our height's going to change, and it's going to go the other way. You know, we're going to have a high change in volume. You know, if this is time is equal to 0, hell yeah. And then time is equal to, you know, 1800 or whatever. For 1 second, we're going to be there. That's going to be the change. This is going to be our change in volume. For 1 second, we're going to run it. The next second is going to be like that. Next second is going to be like that. And pretty soon, I mean, until the thing runs out of juice. And why is that? You know, now we can look at the equation. Well, and isn't that so nice where you can be like, hell yeah, this is perfect equation where I can run it for 1 second, and now I just have this. Change in volume is just a function of, the only thing that's changing in here is the height. So right off the bat, I'm going to have a height of 9 feet. So I can, like right now is a choice time to put that in. I could be like, if I put 9 feet in here, 10 in here, 2 in here, you know what I mean, square root it. And then I have the radius of the hole squared. See, this I don't know, though. You know what I mean? So that's a bummer. That's why this problem's kind of challenging. And then I'm multiplying by pi, and then 0.6, and then there's a negative. This negative threw me for the first, you know, few days on this problem, just because, like, I haven't done a lot of these differential. I think differential and integration problems, they're difficult. You know what I mean? To follow all the logic and the rules of calculus is tricky. But this got me. I will never. Well, no, I'll forget this every day. You know what I mean? To be like, hey, we're changing something. Are we changing it in the positive direction or the negative direction? So we have the tank of water. It's all full, and the tank of water is going down. So that change in volume is going to be a negative quantity. That's where that negative comes from. Alright, hell yeah. So in this equation, like we're supposed to just know, or this is what we're trying to find, but one, you can just say, hey, let's say we know it. I mean, it's a constant, so we're just going to assume that we know it. And then the only thing that this is a function of is the height. And so, and don't let square roots get you down, because if I have this, 2g, and then y, and this is the only thing that's changing, and these are constants. Like, how do I simplify this, or like get the constants out? Well, if you have a square root or any type of thing like that, where you have a product of things in there, then you can use the rule where you can take the square root of 2, the square root of g, the square root of y. You know what I mean? And you can even change. You know, the square root is just to the half power. And I think maybe visually that can help. And now, hell yeah, y is totally isolated. I think visually now you can just see that y is by itself. So even for this problem, the first thing I did is just like, well, let's just get y by itself. And I didn't even put the 1/2 on here, but I could just say it's y to the half, and then times everything else is a constant. So all this jazz is just one big constant I'm going to call c. So now I literally simplified my problem down to, we have a change in volume is going to be some sort of constant times the height, the square root of the height. And when I throw in 9, hell yeah, I'm going to take the square root of 9 as 3. So the first value I'm going to get is the change in volume is going to be that constant times 3. Alright, hell yeah. So now this is my experimentation, because sometimes I forget how to do anything. You know what I mean? You're just like, and I don't want to watch someone do it 100%. So I was just like, well, if I have this, going back to like, well, now I just totally simplified this. I have a differential equation is equal to some constant. Let's just get rid of the constant and just say the constant's 1. I mean, there could be a universe where the constant's 1. And so, booyah. So now I have change in volume divided by change in time is equal to y. You know what I mean? And so that's what I did. I was just like, well, let's separate variables. And now I have y as a function of, so I have, let's see if this is going to work out. Hell yeah, I was wondering where I was going with this. But, yeah, I think what I did was just like, hey, this only jives if y is constant. If y is a constant and the height doesn't change, and we just have all this, like if this is just one big constant, like, because that's cool, that's exactly, and I'm just kind of learning on the fly, but the classic, differential equation would be the change in velocity, change in time is acceleration. And in your physics books, I just got done kind of reviewing this, they'll say acceleration with a little c right here. Acceleration is a constant. It's just a constant value. So then when you separate variables, hell yeah, you got dv is equal to a constant dt. And then when you integrate, well, this constant can just come right out. So you have the integration of dv, you have a constant, and then you have the integration of dt. Alright, hell yeah. I'm so glad I'm doing this, because this is at the most basic. This is where I kind of lose my mind, and it's just like, oh man, like what the hell does this even mean? But this is a good one to go to, because I've actually never done this before, of just being like, hey, dv dt is equal to this constant, this, 9.8 or whatever, g, the acceleration of gravity when you're dropping stuff. And just to say this is an equation, I think some of the simplest equations are just like, hey, this is a function. And is that how you say? I don't even know if that's how you would say it, but we have some sort of independent variable that's a time rate of change of velocity. And I'm trying to get more used to saying like those correct terms, even though when you say them, I think they're meaningless to people that aren't getting it, you know what I mean, anyway. But hell yeah, so we just have a function here. This is kind of our y value. And so we basically have y is equal to mx plus b. But in this case, our, what do we have? We don't have any mx. And is b where it crosses, yeah, oh yeah, that's so fascinating. B is where it crosses the y-axis. B is the y-intercept, but if you just have y is equal to b, man, yeah, even at the most basic, taking like just a linear equation, y is equal to mx plus b, and being like, whoa, this doesn't even have an mx. And so we just have b. So this is y is equal to 9.8, you know what I mean? And that's y is equal to that acceleration constant. And then what we're trying to do is just get to the basic integration. If I do have this dv dt, and then I'm saying it's equal to this value 9.8, why do I get to separate variables, and what does that even mean? Alright, hell yeah. Because, I mean, if I just did this without, you know, like, knowing how to do the nitty gritty, I'd be like, hell yeah. I think I'm going to get V is equal to T plus a constant. And then I'd be like, why? I have no idea. That's just how I was taught. You know, I mean, we can get a little bit better on that down the road. And then you just never do. Anyway, so what we have here is velocity is now a function. Oh, and what the hell did we even do? This is our 9, so I'm sorry. So we have velocity is equal to that constant, so we'd have 9.8, and then we would be t plus a constant. Hell yeah. So this would be my equation for velocity after integrating. But I think it's very useful to be like this integration process before you actually integrate. Like this is such an important. So we have dv is equal to 9.8 dt after separating variables. After saying dv dt is equal to 9.8. And it's so important to see this as an equation. We have y is equal to 9.8. You know, I mean, it's kind of our y is equal to our variable. And you can even throw t to the 0 in here. Because then, you know, this would be like, if it is y is equal to mx plus b, what we would have is y is equal to a slope of 0. We would have 0 to the x to the 0 plus b. Yep. Oh, yeah. So this is where I'm always like, well, can't you just put t to the 0? And that's not true. I think you can get into trouble doing that. But I was just like, hey, just to show that this is still a function of t. When I have acceleration is 9.8, just to kind of show that this independent variable is still t. I think that's important. And I think this is a wrong application to put t to the 0 in here, especially when doing integration and differentiation. I think one way or the other, it might not work out. But I think just to be like, hey, just having an equation with a number, you know, I think that's where it's just like, if I had y is equal to 9.8x squared, or like y is equal to 9.8t squared, you would just undoubtedly like know what to do, potentially more with the integration, with the differentiation. I mean, if you integrate, it goes to t to the cubed. If you differentiate, it goes to t. That's where quadratic, you know, for differentiating and integrating, I think, I'm just going to make a guess that people are able to do stuff like this with certitude. But I think once it comes down to like constants and very simple things, you're just like, well, how do the rules apply? And even in this one, it's just like, again, what is this dependent? And sorry, this is the this is the dependent variable. Acceleration is independent, and I think I said that wrong. Damn it! I'll have to even look that up. Alright, hell yeah. Turn off the camera, turn it back on. We know what we're talking about. So this is the independent variable. It's just independent. It's just time. What's dependent is this. Like this acceleration might be dependent on time. Even though it's a constant, like we said, it's t to the 0, it's really not. It's still dependent on time. It's just this equation is t to the 0. That's kind of how I like to, so that's kind of a good way to wrap it in a bow. Alright, so now we're going to do this very basic integration. But at first I was saying we have this equation. And so, or this relationship, let's see where we're going with this. Hell yeah, no, this is even good for me because we're kind of munching it up a little bit. And that's exactly why I want to do this, is just to, you know, like show my weaknesses so I can improve upon them. Because we just said this was the function. So we have dv dt is equal to 9.8. And I think that's a good place to start and be like, hey, this is a function. And we functioned it. You know what I mean? And then so here's our line. And And what we're going to do, sometimes in integration, they like say, hey, let's go down here to a certain point and then make a slice or whatever. I think sometimes it's useful just to make that slice right away. To be like, hey, I'm going to, what's my value right off the bat? The value right off the bat is 9.8. Okay. And then we can, I don't know what's actually better for this. But, well, yeah, because, yeah, this is so fascinating. Because when I do, like, I always do, like, hey, let's drop something off a cliff. And I'm going to use gravity as 10. I think it's just way easier to use gravity as 10 meters per second squared. And I write it as meters per second. Because now you can see it's like a change in velocity, change in 1 second. And even when you're dropping something off a cliff, we're going to use that same strategy of just like, hey, let's run this for 1 second. And so we have an acceleration, which is a change in velocity. And then so at 0 seconds, t is equal to 0, we have a velocity of 0. And I think, I think you might mess this up simplistically. That time is equal to 1 second, the velocity now is 10. And I think it's really important to at least have that down. Because when we get to our problem of being like, hey, what's our change in volume? Well, that's just a number. And then you might even not fully grasp what that even means. Well, like that's literally going to be the change in volume of the pool. Like that much water is now gone. And then so, it's not full. And then because it's not full, hey, we have a new height. And that's kind of the game that we're going to play with the differential equations and using integration. Booyah. Alright, hell yeah. I'm so glad I'm going over this because this totally explains just the gist of calculus. And so if I drop this thing 1 second later, it has a velocity of 10 meters per second. Cool. Alright, let's do that same process again. How about time is equal to 2 seconds? Our velocity now, we're going to add another 10 meters. Now it's 20 meters per second. Okay, hell yeah. Alright, hell yeah. I think both these problems can be similar. Because here, we're going to run this for a second. And we're going to get our change in volume. Let's say it's, 5. And then we're going to run it for another second. And our change in volume is 4. And then we're going to run it for another second. Our change in volume is 3. And then so, like now, what are we going to use this information for? In this problem, if we got rid of some volume, our height is going to drop. So you can be like, oh, okay, after 1 second, we got rid of that volume. Hey, what's our new height? So this is our new height, And then we're going to have, after another second, we're going to have another new height, and then after another second, another new height. So what would be the equivalent of dropping something off a cliff? Well, maybe you want to know what its distance is. So we're going to say it has a distance, we're going to be 0 meters at the top of the cliff, and we're going to be in this positive direction. We just want to know how far it goes that way in the positive direction. Okay, so for this one, we can kind of intuit it. And this is a good one to use intuition because our change is a constant. And what that means is that we have 0. One way to intuit is just like we have 0 velocity here. We have a speed of 10 meters per second there. We went from 0 to 10. The things that I say on this one, and I use this one just always mentally, is like, well, I didn't go 10 meters per second for that whole second because I was I was 0 here. I didn't go 0 for that full second. And then this one just has a happy medium where if you find the average between 0 and 10, which is 5, that's basically your average speed. And it is. It's exactly your average speed because acceleration, the time rate of change of velocity, dv dt is a constant like 9.8 or 10 in our case when we're just simplifying this. And so your average speed, Alright, hell yeah, we're back. But the camera did cut out, but it just cut out for here. So yeah, what we're getting at from the simplified perspective is if I can find my average speed. And did we talk about that? Because it's linear. It's a linear relationship. So if we go from 0 to 10, the halfway point between 0 to 10 is 5, and that is actually our average speed. If you have an equation that's not linear, then the halfway point's not going to be your average. You know what I mean? That's why differential calculus works, because we just take smaller and smaller slices to where if your thing looked like that, but if I take a small slice right there, you know, and zoom in on that, it almost looks totally straight. And then so then yes, the average right in the middle is going to be perfectly satisfied. Cool. So here we have an average speed of 5 meters per second, and we do that for a second. And so that's going to be our distance traveled in that 1 second. From second 1 to 2, we're going to go from 10 to 20 meters per second. That's our speed, 10 to 20. So we're going to have an average speed of 15 meters per second. And how long did we travel for? Just 1 second. So we're going to travel another 15 feet. You know what I mean? And so we're going to go from 5 meters plus 15. We're going to have a total, now we're going to be at a total distance of 20 meters. And that's where I said, well, it's just like, well, is that what you're interested in? But maybe you're just interested in the change. You know what I mean? We're going to have, in this first second, I'm going to have a change in position of 5 meters. In this second second, because my average speed is 15 for a second, I have a change in distance of 15. And so we can kind of apply that to our equation. What am I interested in? Am I interested in my new height? Or am I interested in the fact that if this is the change in the volume, it's going to be associated with some sort of change in height. You know what I mean? And so those are the values that I might be interested in. Cool. Alright, hell yeah. I want to go through these just to see maybe where I was trying to have an aha moment. Because I kind of have this, I know you can use chain rule. You can have the change in the volume with respect to the change in the height, multiplied by the change in the height with respect to the change in time. And then I was just like, but that got me, that was the conundrum, is just like, how am I going to find the change in height as a function of time? But then through that conundrum, I was just like, oh, well, maybe that's actually what I'm trying to find as a whole thing. So that was kind of fascinating. So we have dv dt was equal to, you know what I mean? I'm just going to say a constant times y, you know what I mean? Y to the half. And that's where I kind of simplified it. I was just like, well, don't I really just have dv dt is equal to, you know, some sort of function of y? We can even neglect the square root. You know, I mean, this is kind of just what I have, and it's just like, well, what if we did dv dy dt, and now this is a function of y. And then I was just like, well, I just don't know if I could figure out how the height changes as a function of time. I just don't know how I would be able to solve for that equation. And that was just the aha moment. And then I was just like, what am I given? I'm given that we have alright, hell yeah. So let's see if we can go over this, because this is the part that I'm just really bad at. And I'm still not just like 100% just going for it. And you don't even need to use the chain rule on this one. I was just like, well, this was the route that I was going. I kind of saw the aha moment that, hey, I can solve for this. And then I was like, well, what's this? This is the change in volume with respect to the change in height. So I can get an equation for the change in volume. And so let's see what we do kind of on this next page. Because we tried to find the change in volume, and we can kind of talk about, you know, how we're going to set this problem up, is that we have, let's say it's brim full, And then this problem states that we're going to lose some volume, that change in volume, due to that equation that we were talking about. So this equation, if I run this for 1 second, is going to be a change in volume. And then so if I can get this volume as a function of this height, so that's kind of the goal. Because it's not the best looking shape. Because as it's a half a sphere to begin with, but as this shape goes down, it's no longer a half a sphere. So we're definitely going to have to use some trigonometry to get an equation for like, hey, what is the volume? And then we're going to get volume as a function of height. So I think that is useful for me to go through before I even try to do some of the equations. That's what I'm trying to learn from the integration and differentiation and calculus perspective, is just be like, cool, let's say I did get volume of this, the remainder water as a function of the height. Like, now what? And what does that even mean? If I have volume as a function of the height, that means that I have an equation that kind of looks like this. Volume as a function of the height is like something height. Cool. You know what I mean? Just maybe, back to volume as a function of the height is just the height. Maybe this is just 1. You know what I mean? And so, at least from that perspective, I know that, sure, this exponent could be anything. We're just trying to simplify things. And then let's go back and let's kind of go back and forth, because I was kind of interested in getting this differential equation. And that was where, because I have to, which is dv dy. So what's that going to be? But then actually, so I need to slow down just a little bit, because how do you, this units don't even match up. You know what I mean? This is volume, meters cubed, and this would be height, meters. So we're not even squared away on the units on here. So how do we get volume as a function of height? Oh, that's a bummer on this one, because I guess I knew how to do the differential part of it. You know what I mean? So that's going to be like, well, how do you know to do that? Well, I guess you just do similar problems. But what we have is, a sphere full of water. And if it's totally full, where it's going to lose its height is just a little disk of material. You know what I mean? So if I take out water, it's all going to go down just by a little bit. And it's going to be this area minus some sort of change in height. And then so that change in height is dy, because this is our y direction. This is going to be our x direction. Our x direction is the radius of the water. So if the water's down here, our x value is going to be the radius. So x is the radius, y is the height. Sometimes that's good to do. But yeah, that's going to be our change in volume. So our change in volume is going to be the area of that circle. So we have pi r squared, and then the height, so it's a dy. And then what did we say our radius is going to be a function, because our radius down here is smaller than our radius right at the start. So we have this differential equation that the change in the volume, if I take out some water, the water level is going to go down, and this flat surface went down just a change in height. So we have the area of that's going to be pi. We're going to say x squared dy. Cool. Now, for differential equations, we need to get this x as a term of the height. So, that's where geometry comes in. If I have a hemispheric bowl full of water, and if I say the height is 9 feet, and it's a hemisphere, half a sphere. If the height is 9 feet, the radius is also 9 feet. So if y is 9, x is 9 feet. Alright, hell yeah. And we'll go through that because we just have an equation of a circle, but you do have to figure out where to put your axes. One of the slicker solutions online just uses Pythagorean's theorem, but I think that's a tricky trick. You know what I mean? I think it's just easier to be like, hey, this is a circle looking from a side. Why not just take the equation of a circle and then shift it to meet our axes? So I kind of do this problem both ways, so that'd be interesting to stay tuned for. But what we want to get is just, hey, this change in volume. And this is, so now we have our three parameters. You know what I mean? We have our length squared, and then here's a length. You know what I mean? So we have an area and a height. That's the definition of like a, look at that. You have, that is your volume. It's whatever you call that, a stacked cylinder. A cylinder with a cylinder. Cool. And we can even just kind of take away variables. We can just say, hey, this nitty gritty is probably going to be a y squared dy. And that's going to be our differential equation there. Even though you go through the process, you're going to pick up a bunch of other junk, you know what I mean? And you have to kind of not get overwhelmed. Alright, hell yeah. So this is where I have a hard time kind of putting things together, you know what I mean, my first go around. And really hard time even just seeing that, hey, this is the change in volume. And it's a function of some differential change in height. And then so I can rearrange this equation to be dv dy is equal to, you know what I mean, something y squared. And so that's kind of what we have going on. And then going back to this chain rule, this is what I was trying to do. And then where does this come from? This is dv dt is that original equation, negative 0.6 pi r squared square root 2gy. And then so we use chain rule to get it into the form. And I'm just saying all this jazz is just a constant, and we're just saying this is equal to y. So that part goes right there. In my process, I call this like c, like cy. So you consider it just cy, a constant times y. But I think this was really important just to figure out what we're doing from the basics of the differential equations to get to that first integral. And what we're seeing is that we're trying to solve for this, so I can move the other things anywhere I want. And so we're right at the place where, hey, I can see that this now is dv dy is equal to just that, you know, y squared. We'll have to get our equation, but but now we kind of know that there's a road to get to this. And then if we know this, then hell yeah. So this is checked off. We totally know that. And this is just going to be some sort of function y. And hell yeah. And it doesn't even, at this point, who cares even what the units are, but we have, you know, I guess we'll keep that y squared. But hell yeah, so this is going to be some sort of y. I don't know if I'm going to keep the squared on it, maybe. This is what we're trying to find. And then we have over here, that was the equation that we were given. Yeah, and oh, this is so interesting because it's just, I even kind of lose my mind in this process. Because cool, it looks like I'm just going to get this to maybe over there or this over there. So now what? So let's look at what this is, because we have dy dt, and then let's say I even do still call this y squared, and this over here, let's call it cy, just so you can remember that that is this equation, just with the constants taken out. Who cares? And now what we have is just you know, something I would like, and that's where I need to take more differential calculus. I mean, do you call this just first order linear differential equation where you can just separate variables and integrate? Well, hell yeah. dt goes upstairs, and we have dy. You know, I mean, we'll keep this y squared there. We're going to divide by this cy, and then we have dt upstairs. And then But yeah, at this point, you know what I mean, I think I have lost all touch of reality with the problem. I'm just using the rules of chain rule, and just the fact that we talked about how multiplying these things, like the math doesn't get wiggy, you know what I mean, it still follows basic principles. Alright, hell yeah. And I even forget how to talk your way through this, but what this is going to give us is it's going to give us an equation y, and it's going to be like hella something something y is equal to our time. And so then we can say that time, so I can input any value of height into this equation, and then it's going to pop out time. So hell yeah, that's exactly what I want, because I want to put a height of 0 in, and then I want to find that time. And so, but then, you know what I mean, through that process, we still have not solved for r. We still don't know what that is, you know what I mean? So this value of constants and this unknown is wrapped up in this value c right there. But at least from like the, you know, what to do with the differential equations, how to put them together, what is, you know what I mean, here we have a function of y, and we're taking a small little chunk of y. And so that's where the integration process works. It's just, you know what I mean, even from this side of the equation, I can't visualize it because we just did a lot of manipulation. But it's the same thing as like this is still a function. And maybe I should go back to that as a function again, just like we did for acceleration. Yeah, that would be very useful. So let's rearrange this equation. Let's say it's dy and then get the dt down there, because that's what we were trying to solve for. We were like, hey, if I could solve for this, what the hell does that even mean? And so if I get the dt downstairs, this cy goes upstairs, this y squared goes right there. And now we have our function. We have the change in height with respect to time. This is going to be my time axis. And what do I think it's going to do? You know what I mean? At time 0, the change in height is going to be negative. So I kind of, well, let's just say this is a negative value. So this is going to be the negative direction. So hell yeah, it's going to start off with a big negative quantity. And once it's actually run out of water, what's going to be the change in height? The change in height as a function of time. I think it actually gets steeper though, because, I don't know. Well, two things going on with this problem that are really difficult. One, we're saying that when it's really high, we're going to have a lot of velocity. And so you're going to have, this is going to be a bigger value. You're going to have a lot of velocity, a lot of change in volume because of that height pushing more water out. So just kind of getting an intuitive perspective. And then so you're going to have more water. But then if we're talking about the change in elevation, this bowl is like hella volume right at the top. And as you go down, you're getting reduced volume. So you actually have probably, you know, those two values will probably overlap. You know, so I can't even tell you. Well, let's see. Change in height. So it's not going to, so right off the bat, it ain't. Well, two things. It's going the fastest, but it's the largest volume. So, I mean, who knows? It could either be shallow. Yeah, let's just say it could be like that, or it could be like that. Or just anywhere in between. I'm going to, I don't even know what I would assume. I think that was just really cool for me to think about that, because hell yeah, it's going to be the most change in volume because the height is tall, and then Torricelli says that the velocity leaving here is going to be the greatest, so every second you're going to have a bigger change in volume. And so you're going, but just the way the hemispheric bowl shape, just because you took away volume doesn't mean your height's going to go down, because you just have so much volume at that level. So let's take a pause on that. And this might be a cool thing to grab. What I just wanted to show here was that this is the differential equation, and it is equation. So if I go to this starting value, you know what I mean? Hell yeah, that's what I'm going to decrease in height. Now this isn't a decrease in volume. This says change in height given a change in time. So let's run it for 1 second, and this is my value for 1 second. Let's run it for another second. Well, now I'm here, and now this is my value for that second. And let's you know, show these. So like right here, this is my 3rd second. We're just going to make it a little bit bigger so you can see. And then my 4th second is this value right there. And then so this is, and I think that is useful for differential equations. Like you put in the change in time as something that, and especially if you can put in 1 right here, then it's just like, hell yeah, that's just the change in height. Every second, that's going to be the value. And so hell yeah, that's going to be the value of the change in, oh well, just a second. Yeah. So 2 things are going on. I'm kind of, this graph, for that value, right at time is equal to 0, gives you a value. That value has units of change in height per change in time. That's where I can say I'm going to run it for 1 second, which is multiplying by that change in time. So that's what you're doing by the integration process. I'm going to say that right at the start, and that's where I think it's more useful, instead of coming out here to some, you know, some variable x, and then making a differential slice dx, I think it's kind of useful. It's the same process that we did with dropping the rock off of the cliff. What the hell happens in the first little bit? I think that's more important than going to some midpoint and then, you know, trying to figure out what the equation is. So right off the bat, you know what I mean? Hell yeah. We were talking about how, oh, and then this, I kind of messed this graph up. There's a chance that if this is the change in height, change in time, I messed this up. There's a chance that it could do this. There's a chance that this graph could do, let's see. I mean, there's a chance that the change in height will never be 0, because you always have some sort of velocity going out, except at the very end. The very end has to approach 0 because you have 0 height, meaning Torricelli says there's 0 velocity. And so you do have approaching 0. But at the start, you're always going to have some sort. You're going to have some sort of negative velocity, or I should say negative change in the velocity of the height. The change, and this is change in height, change in time. So it is the velocity of the height. So if we were perceptible creatures, and you could actually watch this for half hour go down, and you'd be like, ooh, yeah, it's got pretty good velocity now. Oh, it slowed down. Oh, now it picked up in speed. And so that's what I'm thinking could happen. You could have a graph that looks like this, where it actually picks up and then maybe drops off. But it has to reach 0 sum, even if it's sharply, because right at the bottom, that equation says 0 height equals 0 velocity coming out, Torricelli's. All right, I think we're doing pretty good at kind of going over the gist. So let's kind of go back to here, that if at time 0, this equation, this differential equation, you know, it's just a y is equals to whatever. It's just a function is equal to some sort of numbers when we plug in whatever numbers. And so this gives us a value of the velocity of the change in height, change in time. And so, cool. Let's say the velocity is 1 foot per second, a negative 1 foot per second. That means in 1 second, this pool is going to go down 1 foot. I think it's very useful to do things like that, just because the changes are so small. Why not you make them big? And so that's what I just did right there. So I'm going to say this graph gives me a value right at the start of negative 1 foot per second. Then I'm going to run it for 1 second, and that's the integration process. then it means that after this second, I'm down a foot. And that just makes intuitive sense. If I said the change in height was going to be 1 foot per second, run it for a second, we're going to go from 9 to 8. And then after that, once we're at 8 feet, maybe this is less, because obviously it's this equation that's going to be a function of y. I'm going to plug in y and I'm going to get a number, run it for a second, and then I'm going to get a new height. Because if I get, then if it says negative 0.5 feet per second after this first second, cool. I went from 9 to 8. And then after one more second, I went to 8.5. Plug that value in, and maybe it's, 0.3. And then I go to 8.2 feet. All right, hell yeah. So let's try to explain this integration process. Because right off the bat, I'm going to get that value. It's going to be my change in y, change in t. I'm going to run it for 1 second. And what does this give me? This gives me my change in height. Look at it. Change in t cancels, and this is just my change in height over that time over that interval. And the interval doesn't even have to be a time interval. It's whatever that independent part of the equation is. So you can have a differential equation that's dy d, something else. I mean, we started with a dv. Well, we started with a dv dt, but we chain ruled it dv dy dy dt. These are all changes with respect to these independent variables. All right, so where do we get the integration sign? Well, it's basically we just ran it for 1 second, but we know our tank's going to drain in it's going to get almost to the halfway point in 1800 seconds. So maybe let's just extrapolate and say, hey, maybe it takes 3000 seconds for whatever reason to drain this tank. And that's not unreasonable, because we're past the halfway point. You know what I mean? We for sure have way less volume because it's a hemisphere, but Torricelli says our velocity is lower. But you can see that, I don't know, maybe it's intuitive to me, but hell yeah, that tank's going to just drain pretty fast. I don't think it's going to be double 1800. If we get half the height, it's not going to take twice as long, because there literally isn't very much volume, and just because the velocity is not that great, still this thing's going to pump out. And that's just from an intuition perspective. That's all that is. Alright, hell yeah. So if I want to know the height the entire way, then I have to, I have to take this change in height and then plug that new height into my equation, to get the next value. And then I'm going to do the same thing. I'm going to get the dy dt of that next value. Maybe call this one 1 and this one 2. And then I'm going to run that for 1 second. And this is going to give me a new change in height. I'm going to take that new change in height. So if I'm going to say my height is 9 feet, this is 1. I'm going to get y2, and then I'm going to get y3. And I'm going to plug that into this equation that I have. So this differential equation is a function of y. And so that's where the process of being like, well, what are we doing? I'm taking this value and then multiplying it by change in time of 1 second. So I took this part of the equation over there, and then I'm actually getting dy. So that's what we do. We have dy dt is equal to some function y, and then what we're going to do is multiply it by dt, and then when we do that, we get that small piece. And so what we're going to do is we're going to add up all those pieces. And instead of having a change in time of 1 second, we're going to reduce that. Because if I had for the first second, it was 1 feet per second, but my change in time now is just 1/10 of a second. Well, I'm going to have a tenth of a foot. I'm going to go from 9 to 8.9 feet. And then I'm going to take that 8.9 and plug it into my equation and get a new value. It might not be -1, it might be -0.9. And then I'm going to run that for 1/10 of a second. And now I'm going to have 0.09. So I'm now going to go from 8.9 to, let's just use the calculator because I don't want to get stumbled off this. 0.81 feet. And I'm going to put that into my equation. And I think that's very useful to be able to intuit while you're writing the differential equations. Because I know I'm not very good at it. But for whatever reason, I'm good at taking these differential problems and then plugging them into Excel. And it's just fascinating that the differential equations do the exact same thing when I plug them into Excel using numerical methods. It's just difficult for me to see the differential equations do their thing kind of the first go around. Alright, hell yeah. And then there's one more aspect of these differential equations that, or just the integration process that I'm trying to get used to. So in this, we finally broke it down to, we have dy, and did I even get it right? I don't even think I got it right. What the hell? We said this was dy dt, and that's going to be some sort of value after we throw our y in. And dy dt is equal to some sort of value after we throw our y in. And then I'm going to multiply that. That is going to be our speed change of the height. I'm going to multiply that by a small change in time, and that is going to be the change in height. Alright, hell yeah. This is where I thoroughly give up, or I just throw in the towel, because this is the part of the game where I'm just not super solid on. And because to actually do this differential equation to integration, I'm going to go dy dt is some function y. You know, I mean, we got the y upstairs, y squared downstairs. And then when we separate variables, this stuff has to go with the dy. So we have to go dy, you know, and maybe I'm just going to go, you know, this inverse, and then the y squared is going to go upstairs. So we got y squared, y goes downstairs. You know, just kind of flip this. And then the dt goes over here. And then so I'm just going to say this is just some function y prime. No, that would be dumb. But yeah, some function y, well, I'll do the y squared y, because that's what we're kind of used to. And then I just wanted to, anyway, it's alright if it's all. And then so I put my integration signs here. So we separated variables, we do have this dy, and now we're going to integrate. So that process is the same thing we just did. It just doesn't feel like it no more. So I have to go like you know, kind of quiz myself on like, why does it, like, yeah, that's what I don't like about the integration and differential process. At some point, you just kind of, for me, I just kind of lose like touch of like, wait, what's visually happening? Don't see it, but I just know to do this process, because when we do integrate, this goes from, but I think that this is what I want to talk about, the limits of integration. This is going to be my time initial. I think this is good to do time final, or at least, like, maybe forget the final, but time initial to some time t. I think that's more useful, because now I want an equation as a function of time. That time could be anything. It could be right at the beginning. It could be right at the end. You know what I mean? And so I am getting more used to that as writing, doing these integrals. Because you can have an indefinite integral where you just have some sort of constant, and then when you do the problem, you have to put in those parameters. But if you have a definite integral, then, is that right? You don't have to put in the constant after you integrate? Yes, because that's... You can put in the constant, but the constant, yeah, no, that's so funny. You should put in the constant every time, because you are integrating a function. You know, it's like, that's where, if you're starting to use the terms antiderivative, especially with me, I never got introduced to those terms, but you are finding an equation that can be placed anywhere along the y-axis. And then so you have to use initial conditions to figure out where you want to place that equation. But when you do definite integrals, then that placement of that equation is irrelevant, because How is it irrelevant? Yeah, that's interesting. Because integration is like all about finding the area under the curve. But when you integrate, you get an equation that says, hey, like this point is some sort of area like up to. It's like all the area that way. And I might be getting this not quite 100% right. But then this point is like, hey, all the area that way. And then so when we take the difference between, and you know, with respect to the x-axis, because that's also part of it, you're taking the positive area above the x-axis because that's your 0 point. If you wanted to move this axis, that's why you move it with that constant. If you want to get it higher, you're just imaginarily moving your x-axis to account for that. But it doesn't matter if this is down to negative infinity. You know what I mean? All this, all that extra. Oh man, I need to quit while I'm ahead on this. So, alright. So putting in the initial value, and the initial value right here is 0. The variable up here is t. On this side, what do we have? We have y. So this is going to be our height of the pool. Our initial height is 9, and then we just want to go to some arbitrary height. And then when we do this integration process, if we do have the constant integration, it'll pop out. Alright, hell yeah. And again, we're going to move on from this idea of the constant of integration popping out. It's like, that's such a weakness in my understanding of what's going on. But just the fact that it does go away, that's why, like, from a learning perspective, it's just like, well, let's not even figure out what exactly is going on with the equation. And that's where I literally need, I'm going to do it after this video. Just go back to I see where my weakness is. It's the fundamental, properties of integration. And that's where, especially when you have an integration kind of on both sides, like one is, like if you have like dv dt and you're integrating that, this goes to a change in velocity. Like literally, this is v2 minus v1 is equal to, is it just t? Well, if t is 0 to t, hell yeah, it can just be like t. And then your volume might be in this form that your volume, started at one place and got to another. So this is like that's maybe your classic where this is your independent variable that starts at 0 and goes to some time t and is kind of written in this way. And when you do that, you have a change in volume, but your volume can start at any point and it can end at any point, and that's where you get this change in volume, v2 minus v1. But that's where, from figuring out what the problem is, maybe your volume is 0 and you're adding water. So then you just have V1 goes away, and then you can kind of write it as volume is just a function of time, where you just have volume and something time. So that is what trips me up on the integration process, and I'm trying to go back through and learn it from like a more of a nitty gritty, like no shortcuts, like write everything out. Hell yeah. And so from that, even just learning on the fly, what we're going to have here is going to be like a y2, our final height minus our initial height. It's like y2 minus y1 is equal to t. And it's going to be kind of that simple, even though this equation for y is going to be kind of complex and ugly. Okay, hell yeah. So now I think I want to friggin' A, kind of start this problem. But that was a huge introduction. One thing that we can do, though, let me pull up some paper. Alright, hell yeah, I wanted to go through some of this literature, because we do have this equation for the time rate of change of the volume due to Torricelli's. And we're saying it's ideal, but with an adjustment. We are saying there's loss. It's not ideal, it's 0.6. So this equation, and I just threw this into Google AI just to see what the terms are. So this equation describes how the volume of something is changing over time. And we're going to break down the components. Thank God for Google AI. So this part of the equation, change in volume, change in time is how you say it, dV dt. Derivative of volume with respect to time. This is the derivative of volume with respect to time, representing the rate at which the volume is decreasing. So we're taking away negative volume due to that negative, and like I said, always just run it for a second, and that's going to be that change in volume. Now it could be a constant, or it could be a variable that's always changing. In this case, it is changing. So this represents the rate at which the volume is decreasing, indicated by the negative sign. Now we're going to this side of the equation, negative 0.6. This is a constant factor, likely representing some efficiency of that Torricelli's. It's inefficient. It's not ideal. Or it's a discharge coefficient. The negative sign implies that the volume is decreasing. That got me the first time around. We're taking away volume from this pool. All right, pi r squared, that's an area. So, and we should probably go over this first, but we'll go over this first. Pi r squared, this is the area of the circle with radius r. In many fluid dynamics contexts, this term might relate to the cross-sectional area of an opening or a pipe. That's what we have. The opening at the bottom has a radius of r. Now this, square root of 2gh, in this case, square root of 2gy. This term is reminiscent of the velocity obtained from free fall, where g is the acceleration due to gravity and y is the height or depth. This suggests that the flow rate is dependent on the height of the fluid. All right, booyah. Okay, so this Torricelli's law gets derived from the Bernoulli's equation. Bernoulli's equation is an equation for energy, how energy can't be created nor destroyed. Well, especially with fluids, and that makes sense. Like if I have a constant flow of fluid that's not picking up mass, then I'm not adding, energy. I'm not adding extra energy to the system. Bernoulli's equation is ideal, so there's going to be no friction loss due to, and friction can be anything. Like friction is just other molecules vibrating. So that's the general. What I like to think of from the fundamentals is you have mass, like in fluid mechanics, you have chunks of mass that have maybe a velocity. And then in an ideal state, if you have chunks of mass that have velocity, they should maintain that velocity. And then but then the other thing is, in a pipe, maybe you have like a dam on one side and you have a pipe of water. Well, now we can understand that you have a pressure in that pipe, and if you have a pressure here and like no pressure here, then you're going to get a pressure differential. And pressure, like if you have equal pressure, now you just have a chunk of mass that's getting pressured from both sides. It's not going to move. Even if you had a constant velocity and that chunk of mass was getting pressured from both sides, it's still just going to move at that constant rate. So, and that's very difficult to do with like flow, just because you could have an open channel flow that is perfectly level, where water comes in and it doesn't change height for whatever reason, and just has this velocity that maintains, and it just goes on forever. With no friction loss, that would be the case. You don't have any elevation loss, and then that water just moves like that. And in open channel flow, you don't have any pressure behind, you don't have any pressure in front. Maybe that's the case. So yeah, hell yeah. So Bernoulli's equation says we have the pressure of the fluid, and just to get to it, if we have this this pool, there is no pressure. It's not a pressurized pipe. This pressure is like more of like pressurized pipes. So there's no pressure on top of this pool. And then it's difficult to imagine, because you might be like, well, there's going to be hella pressure at the bottom, right? Well, but we're talking about the water already leaving. So the water already leaves the pipe, and then we're going to, pick that water molecule that is atmospheric pressure. So I think that is the trippy trip on this one, is that you have zero pressure at the top, atmospheric, and when water leaves the bottom of this basin, there's zero pressure, it's atmospheric. Okay, and so the rest of Bernoulli's equation is due to the velocity. And what we have is, well, we said if something just has the same velocity, then, you know what I mean? If no forces act on it, it should have the same velocity. And that's what you'd have if you didn't have a change in height. So that's kind of what we went over. So atmospheric pressure with no change in height, hey, that's going to be that ideal situation. It'd be kind of hard to create in reality, of water just moving down a straight, no elevation drop, and then just keep moving. But anyway, so that would be what that is. But our problem says that we don't have any velocity at the start, but we do have height. You know, this pressure is zero, and we don't have any height at the end because we're going to put our datum to be zero. So this is the equation that we get. And Bernoulli's is just an energy equation. I think you lose a lot of the fundamentals of what's going on with, like, hey, I have a chunk of mass, we have forces on it. The forces are going to be gravity pulling that mass down, and then the effect of that is going to be some sort of velocity. And this equation, the energy equations, are just that change from one type of you know, energy to another. Alright, hell yeah. And I think that's useful, I mean, even from my perspective, even like right now. So it's just like, what were we saying? Like the energy in the universe is the same, but then I'm taking some water and I'm dropping it off, or I'm even just taking a rock and dropping it off a cliff. Like the rock didn't have any velocity, and you know, all the energy in the universe is the same, but then when I drop it, now the rock has velocity, but we're saying that there's no extra energy there. It's because if I had to get the rock back to the top of the cliff, I would have to actually put external energy into it. Oh, that's tripping me out. Yeah, so if the rock falls off the cliff, it picks up speed, but that system, that's a closed system. It didn't gain or lose energy because you're just transferring this elevation for speed. If you had to reverse the process, you would actually have to put energy in. Or you could, in an ideal sense, you could take all that velocity. No, this is making more sense. You can take all that velocity and then change it back into the potential energy. That's a bouncing ball. So yeah, I'm glad I got at least that far. Holy hell. Because because that really shows that you can transfer energy into different states. So that's pretty cool. Alright, hell yeah. Sweet, so let's crush this out and do the proof of Torricelli's. So they just say pressure is atmospheric, we covered that, and it's the same on both sides. We can cancel it on both sides. This was 1/2 the rho times the velocity. We have zero velocity at the start, but we do have height. We have zero height at the end, but we do have velocity. So those are the two pieces of the equation. Pressure is the same. And then so the density, they're gonna say we're gonna remove density, and then once we remove density, then we're just gonna solve for V. So this 1/2, 2 goes, so we got 2gh, and then we got square root. So V squared is equal to the square root of 2gh. And that's gonna be our exit velocity of the water out of this pool. So sweet. So this is canceling out rho. We get GH is 1/2 V2 squared, the exit velocity. And then we just solve for the exit velocity. Again, 2gh and then square root. Sweet. And this is Torricelli's law. It states that the speed of the efflux of a fluid from a hole at a depth of h below the free below that height of water, the free surface, is the same as the speed an object would achieve if it just fell from that height h. Hell yeah. Okay, so we'll probably get to this in the end, but I had to double check my answer, and we did that in Excel. So some aspects of here, we have that change in volume. So that's going to be this equation. Oh, yeah. So I need to get faster at this. Change in volume is this equation times the dt's up here. So if I take this equation, which is just the height and then the hole's radius, of that hole, then I'm just going to multiply by the change in time. And the first thing I do is, if I know it's going to take 3,000 seconds, like I never run this more than I can see on the first page. So this is the first iteration. So my time is 100. So I'm going to take that value and then multiply it by 100. We talked about running it for a second, but now I'm going to multiply it by 100 seconds, and that's going to be my change in volume. And then my change in volume, I'm going to use that to find my change in height, because I'm going to get change in height as a function of this change in volume. Once I get the change in height, I'm going to change my height. In that 100 seconds, I'm going to go from 9 to 8.7. And now that I have a new height, I'm going to plug that new height into this equation. And then I'm going to multiply that by another 100 seconds. And that's going to give me another change in velocity. And hell yeah. And we can see that the change in velocity, it looks like it always reduces. I think it always reduces. Even though we said that the change in velocity is going to be based on Torricelli's. So yeah, the change in velocity will always reduce because of Torricelli's. It's this change in height. I was wondering if this change in height, it starts at 0.29, and yes, we go from 0.29 to 0.27, and then we come back up to 0.28. You know what I mean? So we actually change in height pretty fast because of Torricelli's, and then it slows down because, and that makes sense, because we have this tub that's hemisphere, and basically the edges of a hemisphere, they don't change volume. So for, let's say, the first 2 feet, you really don't change the volume. But we are changing, as Torricelli says, hey, your effluent speed reduced. But your change in, I should say change in volume, yes, change in height is now getting slower. So that's going to be at the slowest point. So that does answer that question, that we have the slowest change in height right around that location. And I think some things like these you're not going to be able to pick up on if you just try to solve these problems from like an equation perspective. Like I have one equation, one differential equation, one unknown. This one has 2 kind of unknowns that we're trying to solve for. But hell yeah, that was kind of cool. I'm glad I did this. But now we're going, and then so what this showed was that at 1800 seconds, hell yeah, we're at 4 feet. But this was a double check on reality, because this, I already used the integration to solve for my radius. And then in this dv is a function, if it's dv, it's this times dt. That is a function of the hole at the bottom, the radius of the hole at the bottom of this. And so I already used the integration methods to solve for that, and I just wanted to double check, and I was like, what's the simplest way to double check is to throw this into Excel. Now, could I have done it without solving for R? Yes, but I would have had to set this up with the value here, and I would have just had to use a mountain climber perspective, and that would have been cool to do right off the bat. Set this whole thing up, but have this variable, and it's if I change this value, all these numbers change. And then so what I could do is throw in like 0.1 for the radius. It'd be smaller. In 1800 seconds, it would be at like 6 feet. It wouldn't drain. So then I'd have to increase it. Let's say I went to 0.2 or 0.3. Then this was already drained. So then I have to like reduce it to where that marker, that 1800, which is half hour, makes a height of 4 feet. Alright, hell yeah. And like most problems, like I'm almost running out of steam, but we're gonna try to show you, at least, you know, I already did it, so we can just at least show you the process. So this is like the trickiest trick, I thought, was to do a hemisphere, make your height at any level, and then here's going to be your axis. So we're going to see the bottom of the, and actually we need to start with kind of the fundamentals. Yeah, I mean this was just to do, well, now let's just do it how I did it. But the fundamentals that you need to know is that, yeah, where's the sheet of paper? Alright, hell yeah, we get to this on the second go around, but I think it's useful right off the bat. Because what we're saying is, like, this is the height of the water, and then Torricelli says that that velocity coming out of there is 2gh. You know, that's just kind of ideal. Now that's just the velocity. That's like dropping a rock off this, you know, stack of water, and that's going to be at speed after it passes that line. But now what we want to use is this velocity and get it into a change in volume. So, and then my brother was like, well, use dimensional analysis. What's change in volume? And what we're going to get is like, well, no, we can do this. Because change in volume is like meters cubed. But we also have to be thinking of change in volume, you know, per time. So that's going to be like meters cubed per second. Because if we have velocity, we're going to have meters per second. And my brother's just like, well, what do you need to do to get this? Well, I would need to multiply by meters squared, you know, to get this. And then what's meters squared? That's area. Alright, hell yeah. So right here I have this drawn, that if I have this water coming out as a velocity, and this is where I'm going to say, hey, let's run this for 1 second. So 1 second of water is going to be maybe that much. And then in 1 second I want to know the volume. So that's where I have this. Like, how do you get dV? Well, I'm going to take this rate, velocity, you know, the volume change per second, and I'm going to multiply it by 1 second. So I think that's always useful to do. And if I do that, that actually is this volume of water. And so, cool. But again, we have some sort of velocity of this water. If I run that velocity for 1 second, velocity for, you know, 1 second is going to be distance. And so I'm going to take that 2gh, run it for 1 second. That's going to be my height. So basically velocity is height, you know, just with, you know, it'd be v kh, where k is just, you know, divided by the units. It'd just be, you know, 1 divided by 1 second. Meters per 1 second, you know, where k is even just 1 in that case. But hell yeah. So there you go. So your velocity is going to be square root 2gh. If you run it for 1 second, that's going to be your height of the water leaving. Or, you know, you can say that's the height. And then we want to know the volume. Well, if that's the height of the cylinder, the volume is just going to be the area of that cylinder times the height. And the area of that cylinder is pi r squared. And that's where we get pi r squared h. Hell yeah. So just keep that in mind, because that is going to be the amount of volume that leaves. That's going to be a negative volume that leaves every second. And so you can think of it that way. Or you can think of it as a time rate of change. This is going to be the volume change per second as well. Okay, sweet. So let's go through this process. So again, this was the trick from the internet. You know, I set this up as an equation of a circle. We'll get there because I think we do this kind of twice. But what they have is the height starting from this datum. At the start is just going to be, I'm going to call that capital R. That's going to be 9 feet. When it totally drains, the height is going to be 1 feet. So in this scenario, the height could be any, you know, location, and we're going to call that Y. You know, so when I throw in the variable y into the equation, that's literally going to be the height. And so that's what we have. So now we need to figure out, Like, where does this height touch? Well, it touches the hemisphere right there. And if I'm saying that it starts at the center of this circle, then any place that touches from the center to the outside of a sphere is the radius. So that's where you get this triangle to form. You have this is your radius of 9. You have, but then we gotta, this comes up a lot in trigonometry. I know this height I want to be y, and I know this full height is 9. Well, cool. This height in between is going to be 9 minus y. So I could start here. I could be like 9 minus y. That's going to be the remainder height. So that part of the triangle is 9 minus y. This part of the triangle, I called it x because, I have an xy, but I'm going to say that's just the radius. X is the radius. So this is just the radius of that, disk of water. The surface of the water is a circle, and that's going to be the radius of it. And then so I have, so now what do I want to gain from this? Well, what I need to know, and I guess going through I guess we maybe jump 2 steps ahead. We've already talked about how the change in volume, because, okay, so Torricelli's from the actual height of the water, I'm going to input the height, and I'm going to get out a velocity. That velocity is, going to run it for 1 second. That's going to be the height of that cylinder of water leaving, and that cylinder of water has an area of pi r squared. So that is going to be that change in volume. Alright, so from this diagram, I need to figure out what this change in volume is. And that's where you have the surface of the water, and you just take a thickness of a change in height, just a very small change in height. And we're going to say, even though like the surface of the water changes at this angle, as long as this change in height is really small, then that's going to be a close enough approximation, and it's an exact approximation using the rules of integration. And then so we just need to know the area, the surface area of that water, and we're going to know the radius. So hell yeah, so if we, and what we need is dV is going to be the area of this surface times dy. So that's going to be the differential equation. So a small change in volume is going to be that aspect. And then so what we're going to relate is this change in volume with Torricelli's change in volume. So we can just see that those are at least equal. If one goes down, this one has to go down. Alright, and so the area of this is pi r squared. And this radius, yeah, it's kind of interesting because this radius isn't, that's why I'm going to say this is x. You know what I mean? I'm going to say this is pi x squared. And that's what I have here. So this differential equation is change in volume is pi x squared dy. But this I really can't integrate. If I integrated both sides, I can't integrate. And what's the integration process? It's taking a value on an equation and then having a little change in that. So you get kind of that width. And it's basically the area under the curve. But mainly it's because your function is a rate. And I got to get better at that. We did that a couple times. We said, hey, this is dv dt. So your function is a rate. And then here's your independent variable. And my pen is just juiced out. That sucks. Yeah, I'm feeling the pinch on pens and how much they cost. Holy hell. Alright. Hell yeah. Yeah, so I need to get this x. Okay, so yeah, so this is some sort of function, and then we have a little change in that. But I need to get and I'm just kind of losing my ability to understand calculus. But I need to get this as a function of y. But we have this Pythagorean's relationship. I have 9 you know, if I do the Pythagorean's theorem on this triangle, this squared plus this squared is equal to the radius. And how I like to think of it is, well, if you're trying to go for the hypotenuse, it's always the hypotenuse squared and then the square of the other two, you know, the square of the sides. But if you're trying to get the value of just one of these sides, then it's going to be the hypotenuse squared minus one of the sides squared, you know, and square root everything. Or yeah, I like to think of it as the hypotenuse is the side squared and then the square root of that, you know, because then you can just go right to this equation. And then so if I want to know this side squared, I'm going to take the hypotenuse squared minus that side squared. And so that's what we have. But even right here I just read it as the radius squared is equal to that side squared. Oh yeah, here I just have it as, yeah, if I'm doing the hypotenuse, you know, is equal to, it's the both sides squared. But I'm trying to solve for just this, get it over here, and hell yeah. And then we kind of just, we simplify that, and because I have an x squared anyway, because it's pi x squared, then I don't even have to get this down to the variable x. And so that's what I do. I get x squared is equal to this equation, and that's what we're subbing in. And let's see if I move terms. I get the negative y squared, you know, out front, and then the 18y, and then just kind of the constants right there. So now this is my differential equation. Change in volume is going to be this area times the change in height. And then so I also, you know, took this downstairs to get that dv dy, because that was part of the chain rule. If I had dv dt, then this is dv dy is equal, and dy dt is equal to that negative 0.6 blah 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 square root. And if I'm trying to solve for this, you know, then I can get this whole term dv dy over to this side, you know, divided over here, and then I can, you know what I mean? And so, and this whole thing is just a function of y. So that's kind of that y squared we were talking about. And then this is just a function of y. So once I get all this over there, you know what I mean? I'll probably have to bring it back to where this dy is, and then bring the dt over there. But now I'm kind of on that road of solving, you know, solving this. And that's what I have right here. You know what I mean? I have basically what I just said. dy dt is going to be that main equation. That's going to be this equation up top. And then this equation downstairs, because we got it to the other side. We solve for d change in volume with respect to the height. But once, like I said, once we separate variables, I got to get all this stuff with y downstairs and just the dt by itself up there. Cool. Alright, hell yeah. Let's see how far we did. Yeah, so there you go. And then I started putting the values back in. Because one thing I did is I still took this. This is all a constant. All this, even r squared. You know what I mean? Who cares? This is just y to the 1/2. This is all what I call k. And so, cool. So this is just k y to the 1/2. So we have ky to the 1/2. This, I'm just calling, you know, pi times the big parentheses of stuff. And so, but we still have to, and then, yeah, what do we do? I need to take a look at this. Alright, hell yeah. Yeah, so we show that process. If dy is over here and all this stuff is a function of y, I need to get it back over there. So this ky to the 1/2 goes downstairs, this part goes upstairs, and then the dt goes over there. And so then we can do our integral. And so that's what we do. We set this side is our dt, and we're going to go from initial time is 0 to some just arbitrary time. And so that's going to be our definite integral, if that's how you say it. And then we have, over here we're going to integrate with respect to y, because we have an integration of that dy. And our y term, our initial height is going to be 9, and then we're going to go to some arbitrary height y. and that can be anything from 9 to 0. Cool. And then so the equation on that's going to be pi, and we have, you know, negative, oh yeah. But I simplified it, because when I have pi to this, and I'm going to divide it by y to the 1/2, this becomes negative y to the 1.5. So this 2 goes to 1.5. This is 18y to the 1, and we're going to reduce it by 1/2. So this is now 18y to the 0.5. These constants, those also get divided by a y to the 1/2. So they're like a y to the 0, but then minus 0.5. So that's where we have y to the negative 0.05. 0.5. Hell yeah, and then we still have that constant out front. The k is downstairs, the pi is upstairs, and again, our k term is all of this stuff, even the square root 2g. Cool. And because this is, I mean, you know, this is kind of cool that you can do that to the constants, because then you can kind of see what's the integration process doing to what variables? Like, what variables are changing? Like, obviously, height is changing in this. So when we integrate this, then you just use those simple properties of integration, the power rule. This is going to be y to the 1.5 plus 1 divided by 1.5 plus 1. So that's y to the 2.5 divided by 2.5. So that's what we have. I'm dividing this by 2.5. The y kicks up to a 2.5. We don't have any sign change on these. And then so we would have a sign change if when you bumped it up, you still had a negative, and then you would divide by a negative. But hell yeah, everything is positive. So we have 18y to the 1.5 divided by 1.5. This is this to the y to the, you know, this plus 1 is 0.5 divided by 0.5. And then we integrate, you know what I mean, we have our limits of integration. So you would have a constant in here plus a constant on everything. But then when you do your limits of integration, you're going to do final minus initial. So when you go for your final, it's going to be all this stuff subbing in the final y term, and then still plus the constant, and then you're going to subtract it from the initial term subbed in for y plus the constant. And because you have a constant minus a constant, that's where that constant integration can leave the party. Okay, sweet. But this is your integral, and this is you know, and then one aspect of the problem was just like, well, what do we have? And this side of the equation is going to be t minus t naught, which is t minus 0, which is just t. So now we have an equation of t as a function of y. I'm going to input any y from 9 to 0, and then it's going to output a time. And then this is where we can solve for r, because our term right here, our constant, was negative 0.6 pi r squared square root 2g. G is known, pi is known, but this r term isn't known. So I'm going to say that this constant is that negative 0.6 pi r squared square root 2g. And so that's what we have right here. And then so what I'm going to, from our problem statement, it says at a height of 4 feet, we have a time of 1800 seconds. That's half hour. So we have half hour is 4 feet. So I can throw in 4s everywhere here. I can throw in 1800. We have pi. We have this k term, which is all known except r squared. So that's what I'm going to do. I'm going to take, and I'm saying this is the parentheses here. I'm going to say pi divided by k is now a c term. Oh, what am I going to say? I'm going to say that this constant is now c r squared. So k. So I'm going to change this constant k into a c r squared because I want to solve for r at some point, or solve for r squared. So the c term is going to be everything right here. That's what c is equal to. Okay, hell yeah. So then, and that term's right there. And that's in the bottom, so I need to pull it to the top. So that's where I take, or Or what do I do? Alright, I don't mind walking through this, but it feels like I did the wrong thing and got the right answer. You know what I mean? Sometimes that happens. Yeah, I might have done the wrong thing on this, but just didn't solve it at this point. So yeah, because I was just like, okay, I'm almost there. But if I'm saying K is CR squared, I would have CR squared down here. And if I wanted to get, I would get CR squared T up there is equal to, you know what I mean, this. And if I want to get R by itself, I would have 1 divided by C divided by T. I would have 1 divided by TC, the square root of that. So yeah, so this C should be downstairs probably. So that's kind of just a mistake there. Oh yeah, let's get some more water. Okay, but that's where... This is the point in the problem that I'm just like, okay, hell yeah, I can solve it. I got all my constants out of the way. You know, I just solved for the variables that I needed. Even though this, I treat it as a constant because it's not a variable. That radius is always the same. Yeah, so that's the radius of the hole, and that just always stays the same. So now I wanted to dive into just a little bit more of kind of like what's going on from the differential perspective. You have a big chunk of water. Ours is a hemisphere, but you can just think of it as a cube. As the volume is leaving, so let's say like that much volume leaves, I just wanted to show a visual picture of like, hey, that volume is now gone, but it's gone out of the top. And then once like all these top bricks go, then you can say we have a change in height, and so that's a change in Y. And so, cool. Then yeah, let's see what we do here. I use that... Oh yeah, and that's the only thing. I do want to cover this because it's on this page. This is where. Oh yeah, we'll get there in a sec. Yeah, because this is 5. We're gonna go to 6 after this. Okay, so I guess I use that radius. What are we doing? Yeah, the area, the surface area of the change in volume. I'm trying to get the change in volume equation. And I'm just saying that the change in volume is that area, and then times the thickness. So that's what I have. And then from this perspective, I just want to put a delta V on it, because I don't want to use a differential process, because I'm really interested in plugging this thing into Excel. Of just like, hey, could I solve this with Excel? And so, so I have a change in volume is the area times the change in height. So that's what I have. And then I have the equation that says the change in volume, change in T, is this initial equation. I can get a better sheet going. Is this equation right here. This is change in volume, change in T. And even this, I can say, is change in volume, change in T. It's not going to be 100% accurate, but when I throw it into Excel, it's plenty accurate as long as my change in T is reasonably small. So that's what I have right there. And I was just trying to go through the process of equating these two. And so I probably don't do it till page 7. But yeah. So let's see. So I have, we talked about how the water leaves. And then what I want to do is go over the hemisphere. Because the first way I did it, I always saw this was a half, it's just a circle. You know, it's just the equation of a circle. And so I wanted to put some parameters on this. And so if I did this and this, you know, as my first, oh yeah, it's kind of fast. This is kind of tricky. Because it's just like, well, I don't know how to set up, like if this is my x variable, how do I go up to there? I'm not used to that. Like, I'm more used to being like, hey, so I just set up my xy coordinate, xy, and I'm just really familiar with this being the equation of a circle. This is going to be y is the square root of r squared minus x squared. You know what I mean? I'm just familiar with that. And we can even kind of see where that comes from because, well, if I set this is x and this is So this is the radius, this is x and y. Then we have a Pythagorean's theorem. So I have x squared plus y squared is equal to r squared, and then I can just see that solving for y is r squared minus x squared square root. So it's just kind of fascinating that that is the equation of that that line right there, that half circle. All right, hell yeah. All right, and this is a good time to look at, you know, even just where this well, we're trying to get this equation. So even just looking at this hemisphere of water, when x is 0, our radius is 9. So that's what we have right here. But on this thing, you know, I mean, what is this representing? Because I know that this is a circle, but how could I represent this right here? Well, I could say if x is 0, that's 9. Maybe that's going to be, or do I even want to do it that way? Yeah, this was kind of interesting. Oh yeah, I kind of want to do it the other way, where it's just like I want to call, like, I maybe want to use this as my x variable for, that's what I did. I used this as my x variable just for a little while and said that, hey, if this is, because this is the thing tipped over. Because if I change this like this, you're like, oh, okay, this is my x variable. And then I'm going to say, and this is the same thing as, you know, I'm just familiar with it like this. So we have x and y. And then when x is, so, and then what we have is like, hey, when x is 9, that's this way, the height is the radius. You know, not, I mean, yeah, so when x is equal to 9, this area of this circle is also 9. And so right here I have, like, if x is equal to 9, that radius is 0. So I need to shift this. Man, brutal. Easier said than done. And it's really hard for me to even follow, like, what I was doing. But I definitely got down to putting the circle here. Moving the oh yeah, I apologize. Alright, hell yeah. But so I set this, you know, this is kind of the typical x-axis. I'll call it x prime, y prime. But I'm setting this as my height. So this is going to be 9. When this is 9, the surface area, the radius of that surface area is r, or 9 as well. And when the height is 0, the radius is 0. So I need to have that. Because right here, if this is my equation, if I throw in 9, I'm going to have a height of 0. And then so basically if I throw in a value of 9, I need my radius to be r. And then so this equation, if I already have an r here. So if I throw in x is equal to 9, then I have to have like 9 minus 9. So for that value, I'm going to have, I want to throw in the value of 9, and then I'm going to subtract, so I have x is the value I'm going to throw in, I'm going to have x minus 9. And that is the term that I'm going to, oh, I didn't even do it right, damn it. So I'm going to start with 9 and then subtract x. I guess it doesn't matter, actually. I'm glad I did that, because we're squaring it anyway. If I had x, alright, hell yeah. So, yeah, we're on our last battery. So we'll see if we can do this. But yeah, that was kind of interesting that, yes, if I throw in a value of 9, I want this equation just to be r. So we have r squared square root. So if I throw in a value of 9, I need this to go to 0. And so we do that by doing 9 minus or x minus 9. It doesn't matter, because if I have a negative here, negative value, and I square it, that's going to go away. So yeah, it's just kind of fascinating that there's even 2 ways to do that. But that shifts, that's what shifts this equation to where this now works out. So when I throw in a value of 0 here, I'm going to have 9 squared, and it's going to be 9 squared minus 9 squared, so that's going to be 0, and then we get that value. So there you go. So kind of just two ways to do this. So you could think of this as a half circle that you're shifting, and you just have to shift it along the x-axis, and that's what we do. But that's where I don't like to memorize things. You know what I mean? I like to be like, hey, pick a couple points, and then is this going to be a negative or a positive, or how's that going to work out? Cool. Alright, hell yeah. And going over this, I was thinking that I probably already thought this was like the change in volume with the change in time of 1 second. Because I didn't even write, I just have change in volume here. But this should be change in volume, change in time. But if I'm setting the change in time to be 1 second, then I have a change in volume. And that's where I was trying to relate, kind of just like putting it all together. Because this is that change in volume, that time rate of change in volume, and using this equation, that's what funny, I don't even have, like, I know that yeah, what are we trying to do? This is the area of this disk dy, and the area of that disk is pi x squared, so it's pi r squared dy, and then so here's our x term, and we're going to square it. And so yeah, it's just fascinating. Maybe I'm missing a sheet of paper. But maybe I just kind of knew what the hell I was doing, and I just went to right here. So let's see if we can connect the dots. So I have change in volume is going to be the area times dy, which is pi x squared dy, which is pi, and it's going to be this equation minus the square root. So we have this. We have pi r squared minus 9 minus y squared. Oh yeah, and then oh yeah, I was saying this is x, but you know, on our the way this is set up, this is going to be my height y. You know what I mean? So I'm just used to being like, hey, this is y, this is x. But for this problem, this has to be height. So we're just looking like, hey, this is the height of the water, even though we're just looking at it sideways. If we want to turn this upright, then we have to say it looks like this. And we can do that as well. So anyway, so yeah, so this value, instead of being x, is just y. That's the only change there. Cool. So we have the change in volume. And this is change in volume given a height. And so let's see if we can throw this all together. We said the time rate of change of, we were given that equation. That was, some sort of equation. But I think what we're doing is, just a second. Oh yeah, that's why I realized this problem is really simple. You know what I mean? Or you didn't have to use chain rule whatsoever. Because if I have dv dt is equal to negative 0.6 pi r squared, and this r is the orifice hole, and then 2gy, and I'm saying dv is the change in volume is this, then I can and then this change in volume, I'm missing a dy there. So hell yeah. Brutal. So this dv I'm throwing in right there. And then I'll probably have to take this downstairs and take the dt upstairs. So that's what we do. Let's see if we do it in one step right here. Probably not, so let's write it out. So I have this dv pi r squared minus 9 minus y squared dy divided by negative 0.6 pi r squared square root. I'm going to go 2g and then y to the 1/2 is equal to dt. Now I can integrate from initial time 0, and then we have a dy, so I can integrate from initial height, y initial is 9, to some sort of arbitrary height. Cool. And so what we can do is we can FOIL this. This is going to be 9 minus y squared. How I like to do this is just it's going to be y squared plus 81. Well, we can do the second term first. It's going to be negative 18y plus 81. That's going to be a negative all that, so I'm going to have negative y squared plus 18y minus 81. And then we have minus r squared. If I realize this, r squared is 9 squared, so those cancel. So I literally have that. That would have been useful, kind of the first rodeo. Pi's cancel. And then so we have, this gets factored in upstairs. So we have negative y to the 1.5 plus 18 y to the 0.5. And then we're still dividing by, well, that's just dy. And then we have constants of integration that we can get outside. So we have negative 1 divided by negative 0.6 square root 2g. And then we even have an r right there. And then when we integrate this, we get negative y to the 2.5 divided by 2.5 plus 18y to the 1.5 divided by 1.5. Oh, and again, this is dt over here to t. I'm just going to do that one. It's going to be, t minus t naught 0, so we just have t. This again is still going to be 9 to y. And so we did that part. So we have initial 9 to y. And then we have all those constants. And so we have the constants of 1 divided by negative 0.6 r, and it's r squared, sorry about that, r squared square root 2g is equal to, now we got to do this. So it's going to be negative, we got negative y to the 2.5, and I'm going to do that in kind of parentheses, divided by 2.5, and then we're going to have, minus a minus, so it's going to be plus y to the 9, so I don't lose my friggin' mind, I'm going to do this negative as a negative 1, I kind of like to do that, and then I'm going to do y to the 2.5 minus y to the 9. I like to do that. That's way slicker, and then 2.5. So you just kind of factor that out. This is going to be 18 y to the same thing, y to the 1.5 minus minus 9 to the 1.5. And we did something wrong. This is 9 to the 2.5. Sorry about that. And this is 9 to the 1.5. Hell yeah, and divided by 1.5. So you're just putting the y in for the first term and then subtracting 9 in for the second term. Alright, hell yeah. And so this is all equal to t. So I could I could just say t is equal to, so these constants. Oh yeah, and this is where we want to get r squared by itself, or just r by itself. And why do we do that? Because our time is going to be 1800 seconds when y is 4 feet. You know what I mean? So so this side is with our constants, and then this is our time. And so what do we want to do? We want to get our constants upstairs, at least the r squared. So we're going to have 1 divided by negative 0.6 square root 2 times 9.81. Let's see. And then we're going to multiply it by this, which is negative 1. And this is going to be 4 to the 2.5 minus 9 to the 2.5 divided by 2.5 plus 18, 4 to the 1.5 minus 9 to the 1.5 divided by 1.5. Cool, and that's going to equal r. So we're going to, well, r squared, so we're going to take the square root of everything. And hell yeah, hopefully this works. Or maybe, hopefully I made a mistake, who knows. I'm going to do maybe this first. 4 to the 1.5 minus 9 to the 1.5. Times 18 divided by 1.5. I'm just going to store that as x. I'm going to do this. 4 to the 2.5 minus 9 to the 2.5 divided by 2.5 times negative 1. I'm going to go x plus that. I'm going to store that as x. I'm going to divide by negative 0.6. I'm going to divide by the square root of 2 times 9.81. Hell yeah. And then I'm going to take the square root of that. And hell yeah, we made mistakes. Bummer. Oh yeah, no, we got this because we did not, we didn't use our pi term. So let's pull up a sheet. And so our constant was negative 0.6 pi. And then it was r squared square root 2g. But that's not going to help either. But we should have a pi down here as well. Negative 0.6 pi. Bummer. Alright, this is brutal. Because this equation worked. Where we had... yeah, we're probably picking up 2 pi terms, so we gotta keep track of that, and we're just getting hella messy. Brutal. Alright, hell yeah, we made no mistakes, but we just forgot to divide by the 1800 for the time. So let's walk through, because the process is fairly simple. We're taking the change in volume, which is some sort of area of that surface times some sort of thickness. I'm going to take the time rate of change, I'm going to multiply this by a dt. So I'm going to say, hey, it's some constant y to the 1/2 dt. And then sweet. And then I'm going to say this area is pi, and I said it was like pi x squared, and that was kind of that variable. And then that variable, we were able to, let's see, we were able to get that. So that x squared is going to be, you know, that is the radius. X is the radius as a function of the height. You know what I mean? So this value is the radius as the function of the height. And on this side, we do have a pi right here. So I'm going to cancel the pi's. And then that's where we get kind of that integration equation where we get the y's to the 2.5, y's to the 1.5. And then that's going to equal these constants, which is negative 0.6, no more pi, but we do have r squared, and then the square root of 2g. And then we have integration for t. And so this is what we have. When I throw in a time of 1800 seconds, g of 9.81, and then the y's of 4 into that equation, I want to solve for r. And so how we can do that is we can say that r is the square root. I'm going to have that thing, and then I'm going to have, I'm going to divide by these constants. So I'm going to divide by 1, negative 0.6 square root 2g. So we were basically there, but I just didn't divide by also t. So there you go. So we had We were so close. And yeah, and so maybe we'll just go over it one more time. Alright, and here was one of the equations I was using for that. So I'm going to do -1. We'll do -1, and then we have, and then this is our y. So we're going to do 4 to the 2.5, that's y final, minus y initial is 9 to the 2.5. You know, that's kind of the integration process. So this is after taking the integral, this is evaluating from final to initial. Initial is 9. Final is that 4 feet, because that's part of the equation. It says at 4 feet the tank is 1800. Cool. So I'm going to have that value plus 18 divided by 1.5. And then we have 4 to the 1.5 minus 9 to the 1.5. Cool, that's that term. This term is 0 because r squared is 9. 9 squared minus 81 is 0. So hell yeah, so we get this for that value. And now we're going to see what our constants are. So that's that value right there. I'm going to divide by -0.6. I'm going to divide by the square root of 2 times 9.81. And then I'm going to divide by 1800. And then I'm going to take the square root of it. Okay, hell yeah. So we get 0.059. And I even think that's wrong. I mean, we're just making some sort of small error, so I need to figure that out. Alright, hell yeah. I just plugged this in again, you know what I mean? And we get a way different value. So I think we should be good here. So this value is -143.6. I'm going to divide by 1800. Then I'm going to divide by -0.6, divide by the square root of 2 times 9.81. And then I'm going to take the square root of that. Hell yeah. Okay, so that's the answer. I don't know what kind of small tic-tac mistakes I was making. But booyah. So here's the answer. This is the radius in feet. And then once we know the radius in feet, I'm going to sub that back into here. So I'm going to store this as alpha r. And then I'm going to solve for time. And then so this equation is, let's see what this equation is. You know, it's this time divided by these constants. And the pi's canceled though, so we don't need those. So let's see if we can do this. So we're going to use this equation right here. Let's do the constants first. I'm going to have 1, and we want to know the time that it's empty. So 1 divided by -0.6. 1 divided by the square root of 2 times 9.81. Cool. Okay, hell yeah. Those are those two constants. We have 1 divided by r squared, the radius squared. Okay, so we got our constants the other side. Now we just have time. And now we're going to multiply it by, you know what I mean, this. That was kind of that integral process. And we're going to have -1 divided by 2.5. And then we're going to have, we just have a 0 here. So we're just going to have 9 to the 2.5. So negative, and then 9 to the 2.5. Watch out on the negatives in your calculator. Who knows what they do. Plus 18 divided by 1.5. And then this is going to be negative parentheses 9 to the 1.5. And then that's it. And then another parentheses. And sweet. So we have 2,842. And that's going to be the seconds. So I don't even know where I even wrote that down. But we can even check our Excel. So let's see what I can get first. Hell yes, this is what I get first. 2,000. So I have 2,840. So I'm going to go here 2,800. And hell Hell yeah. Well, this is running a little high, so let's check. Let's see what we got. All right, hell yeah. So I pulled up the Excel numbers, and you know what I mean. I think we used a time of 1 second. Yeah, 1 second intervals. And this shows 284, somewhere between 284 and 285. Our answer is 284, almost 2843. And the reason why the discrepancy, and that's why we were off on this one, you know what I mean? Because if I choose a time rate of 100, then this is, oh, that's fascinating. It actually says it drains slower using, you know, it seems like you're using the faster times, but that's interesting. But and I think we explored that because your change in height gets slower towards the middle. And so because it gets slower towards the middle and using big change in time gaps, that means that you're underestimating the change. It should be more change, but there is less just because the height goes down and your change in y goes down. Yeah, because this you have a lot of change in y, and then at the end you have a lot of change in y. But in here, this slow part probably adds to the fact that when you do the process of numerical methods, you know, getting your change in time to be just bigger quantities, you are saying it's draining slower. And so right here, I would say that it's draining between 2,000, pretty close to 2,900, and so ours is 2,840. But then when we hone it down to doing it by 1 second, then we're really close. And I think, I mean, this is the only way that I would feel comfortable, you know, like, but I'm just going to say, like, getting the right answer. But doing this process of putting it into Excel, you're still putting in the same equations. You're putting in the change in velocity as a function of y. That's what we saw. That's what we did the disks. Well, actually, no, this is the change in velocity. Let's see. This change in velocity is this equation. So it's basically, this equation is change in velocity. So as a function of y, using this equation, using the radius, this radius, and then multiplying by this change in t. So the change in t here is 100 seconds, and that's going to be the change in velocity. And then using the change in y equation. Alright, hell yeah, that sucked. Because I was just like, where the hell does this dy equation comes from? It comes from the dv dy equation that we came up with, which was, this was the area times the, so we have the area times the thickness, so we had area dy, and yeah, so that was the change in, oh, this sucks. Nope, see, I get these mixed up all the time. This is not dv dy. dv is just the area. The change in volume is that surface area times the change in thickness. So that's where writing these differential equations, like one like this, and then saying that dv dy is equal to, you know what I mean, that area. But this area is that pi x squared. That's going to be that pi, and this was the r squared minus x minus 9 squared. You know, x minus y minus 9 squared. So that's this value right there. Well, let's see. This is dv is equal to this area dy. So dy is equal to this value dv divided by pi r squared minus, you know, 9 minus y squared. So that's what we had there. So hell yeah. I had to go look that up. I was about ready to lose my mind. I was just like, holy Toledo. So that's fascinating. I can get done with the whole problem and be like, I don't even know what's going on. So that's really, yeah, integral calculus is crazy. But it's kind of fun. And I really enjoy the fact that I can just use numerical methods in Excel and get that answer. So hell yeah, that's how I get that change in height. Once I get that change in height, I'm going to set that new height. Once I set that new height, I'm going to get the new change in volume, because I'm going to say that's this equation with this new height, new times that change in t. That's going to be the independent variable. That doesn't change. So it's just really fascinating that you only have 3 different things going on. You're changing the volume, you're finding the change in height based upon the change in volume, and you know what I mean? And that kind of seems like chain rule-esque. dv dt is equal to dv dy, dy dt, and the change in height is a function of time. That's kind of what you're after, right? I mean, didn't we get height as a function of time? We had something something height and then time. I remember that. You know what I mean? We had y to the 2.5 minus 9 to the 2.5. So that was our function of y, and that was time. But for whatever reason, it's really hard for me to see that pop when I just see d's all over the place. You know what I mean? So hell yeah, I think I'm thoroughly done with this. We did not master it, but we talked our way through it. We didn't get stumbled up too much. I don't know, what do you think? 3-hour video? Who the hell knows? But this one, I don't know, I just thought it was pretty sweet. I wish I could speak better words more fluently, but I think we do a pretty good job. So hell yeah, just another, you know what I mean, patient old video to go learn how to teach. But this is the learning process. Let's say I didn't know how to do 20 subjects this well. And I'm pretty decent at this. And you know what I mean? Like, how do you teach something you're not very good at? That's no one knows. Anyway, but we do a pretty good job. Thanks for joining me. Hell yeah.